because I would design it to be very good at OpenCL, right? So once a standard like that does emerge and get adopted, it actually influences how the hardware itself is built. And you can have a nice, positive reinforcing style.
And if I may say it inside, IBM had an incredible advantage on MPI because you had Mark Snur, and who basically spent full time on the standard, while the rest of us were just trying to keep, make sure that something worked on other things, because his agenda was to get it to work well on IBMs. And the rest of us were just, Mark is a sharp guy, and I can say it now, he's no longer at IBM, he's down in Illinois, but I'm sure you know a little bit about that. Sorry, I had to mention that. And that gave it IBM an advantage, of course, and MPI. I saw it from the inside, I can verify it.
Yep. Good. All right. I have a conclusion slide that we've already covered, so I think I'll leave it here.
Any more questions?
And what is the SPE optimized accelerator?
So I think, and I try to show that a little bit with the, I shouldn't walk too far away from it. The only design decision inside the SPE that I think is sort of clearly driven towards a particular set of applications, actually something I haven't talked about, which is, we decided not to put a cache between the local store and the exit and the data flow.
No.
So a load on the cell processor is 6 cycles. If you're trying to build, a truly general purpose core, you tend to look at spec int as one of the things that you have to be really good at, sort of out of the box. I think spec int, is load compare add branch type, fairly, a lot of things are fairly irregular. They tend to favor, a fairly low latency. So, 2 cycles, I think, is a nice number. In the case of cell, we did think that it was going to be, and this is not an architecture decision, this is a microarchitecture decision, right? So in the case of cell, we did feel that it was probably going to be used mostly for computationally intensive workloads, where we would be able to identify a loop and unroll the loop. We had 128 general purpose registers because we had, unified the register file. So we didn't feel the need to put that cache there. That drives it a little bit towards computationally intensive workloads. Other than that, I would say that there isn't, the only thing that makes cell specific to certain workloads is inertia and what is out there. This idea of locality is not a domain-specific idea. I
think the question, would you could have cached there today, knowing now?
Well, actually, yeah.
Oh, that's I think it's a decent question.
No, it certainly it depends. If it was a system that was going to go into a game system primarily, probably not.
No,
but if I was going to, if this was going to be my general purpose machine, then probably yes.
Well, just the reason I'm asking is because look, that's what NVIDIA has done since then, right?
Yeah. Now in the case of those kinds of processors, and to some extent also Blue Gene, fundamentally there is another way to hide memory latency, right? And when people started with microprocessors, this idea of sticking your hand out and saying a hammer was actually perfectly reasonable because memory was a cycle away, right? So everything was sort of right there, right? So it's we've been trying to deal with what people call the memory wall. Throwing lots of small threads at it is another way to deal with it.
And the question is, if you have space to add a cache to real estate, how that compares to having instead of 128 registers to have, let's say, a 0-8 state fast memory right there instead of a cache.
Yeah, but you can't. Yes, but you can't. There is there really are only two ways that I know how to deal with. If you're working on a large problem, right, and a lot of it is sort of out there in memory, you know, take multi-core effects, is 1,000 cycles away or so. Right? There are only two ways that I know how to deal with. Right? One of them is, you know, indeed to sort of, we called it DMA. It was an unfortunate name. It makes people think that it's a very expensive operation. It goes to I/O space or something. It's really like a streaming load, right? And it takes just as long as a load, would in many cases. And you can have many threads. And then, yes, you can put caches in there, but they, you know, it doesn't fundamentally change the problem. You know, if the stuff that you need is out there, then
You will have to pay the price of bringing it in.
yeah. It doesn't mean that caches are bad. That caches are a big component of what we've needed to do to make, you know, to make single thread performance grow. And you know the ease of programming benefits that we got from that, you know, were worth a lot. But you can't. I don't think you can get your way out of the efficiency problem by using even bigger caches, because caches sort of fundamentally don't give you that one-on-one return.
I was not asking for a bigger cache, more like local memory that the programmer has access to that.
Well,
So
but
it's
that's,
kind of an
sure,
extension register, but not cache that's automatically loaded.
And certainly I won't argue that the local store, the way we architected it in Cell, is the only way to do it, right? So, you know, you could have, you know, people have thought about taking a conventional cache architecture and, you know, being able to lock down, you know, certain regions of an L2 cache, for example, and use them as local memory. You know, that kind of stuff is also.
Because the users were opting to put their task into shared memory, does that mean that there wasn't an efficient way to communicate between the different?
The reason people did it, so it's sort of intrinsically less efficient, right? It just makes it easier to maintain your code. So if I go to this H.264 example, right? If you've parceled it up into little pieces that go sit on shared memory, you know, if I now want to use a bigger image and it turns out that I need, you know, instead of needing only one SPE for that phase, you know, I need 5 SPEs. If you've worked it through shared memory, it's relatively easy to change your program to handle a larger problem. And it was that kind of fine-tuning there, sort of for every different configuration, there was a different kind of SPE pipeline that people wanted that sort of made people give up on that pretty quickly. In the case of, I think that the best fast Fourier transforms that people have written for Cell do use this and get close to a factor of 2 performance improvement over the best FFTs that didn't use local to store transfer. Now, again, you know, you have to qualify that because there's a million different kinds of FFTs. And the FFTs are interesting because they tend to have a fairly good balance between computational requirements and memory bandwidth requirements. Well, this was quite a way.
That one was very hard.
This one was quite a ways beyond what people.
Yeah, you know what I'm saying, but you can't think of, I mean, in general application.
Yes, yes.
But obviously, if you're talking about that kind of stuff, you're doing it.
This was.
You're creating the codelets, you know what I'm saying?
Yeah, they were absolutely. Yes.
Okay. But that's you know, you have a codelet, you can use that.
Right.
Okay.
The SPE, was that on a per chip basis, or was that on a per
I'm sorry,
SPE?
I missed the very beginning of your question.
Pardon, when you were comparing
the efficiency?
the Tesla, I said Tegra with the NVIDIA Tesla.
Oh, okay. So you mean like in performance per transistor or something like that between
Well,
cells?
you had a.
So that was at a chip level.
Okay. So then was that? I mean, that Tesla was like 100.
But it was a previous generation Tesla. It was like the equivalent of an M1000. I don't know what the
This
Or
looks-
1070, I think right now they're in the 2000.
Yeah, 2000.
So it was roughly half of the biggest Tesla you could buy today. and today, you know, it would outperform the cell processor on that kind of thing by a factor of 2.